All right, I wanted to provide a real quick clarification and some hints on homework 8.3. There's a little bit of a wording, I don't want to say a wording issue, but the way that the problem's worded in the textbook for problem 2, I thought might have been a little confusing, and so I kind of wanted to give some clarification and then ultimately show you what I'm after. But first off, so these two hints are specifically talking about problem 2, not problem 1. But let me start off with the first hint, and that's the area, related to the area. So when we're talking about a pressure vessel, right? So here's the pressure vessel, right? And in this particular problem, there's an applied load like this, so we'll call it F, right? So there's going to be a stress from that load that's computed as F over A, okay? But the question is, what's the area, right? So if you cut a section through the vessel and look at the cross section, you're going to get this, right? And ultimately what you're interested in is determining that cross-sectional area. Well, because the pressure vessels are just that, they're thin, they're thin-walled, you could use the outer diameter minus the inner diameter squared, but there's actually a pretty easy shortcut for computing the area, and I propose that the area of the vessel is just the circumference multiplied by the thickness. In other words, the circumference, so imagine, take a look at that formula. So the circumference is the length of the vessel along that circular path, and if we take that length and just multiply it by the thickness, that's the area. Imagine taking this vessel, cutting it, and then laying it out as if it was a sheet. It's just the area of that sheet. So you can compute this as just pi times the diameter times the thickness. So you can calculate the or I should say 2 pi r t, whichever way you want to do it. But the point is, you can calculate the area very easily, and so you do need that for this problem. And I just wanted to mention that that's a really easy shortcut for computing the area. Now, the second part, I kind of wanted to explain where it says consider in-plane stresses only. So what we're essentially talking about is that here's your stress state, and ultimately what we're considering is, stress like this, and taking these and saying, here's my sigma x, here's my sigma y, here's my tau xy, and then feeding those into Mohr's circle to get this, this, and this. And this was something I wanted to mention in class today, but it kind of slipped my mind. But the idea is that this is considering only stresses in the plane, right? Now, there are instances where you could, in a pressure vessel, get stresses out of the plane, right? But if you look at the actual values, those stresses are less than what you get in the plane. So, for example, and the easiest thing to do is to follow sort of what's in the textbook. And so if you look at the stresses that are listed on page 827, you can see where we have, maximum in-plane shear stresses and maximum out-of-plane shear stresses, and they're listed, I get, a little differently. What my ultimate interest is for this problem is I want you to take the what we did in class today to compute sigma 1 and sigma 2, but then superimpose that with sigma y. And what you're going to get is a stress state, and then from that stress state compute maximum stresses. And ultimately what we're interested in this problem is to take this tau max and set it equal to the allowable stress to determine the required pressure. Now, what's going to happen is, because of the way the problem's worded, the textbook was looking for something a little different, and so as a result, what you're going to get is going to be a slightly different answer than what's listed in the back of the book. So in order to keep things simple, I just updated the assignment on Blackboard, and I put, this is about what you should get. And I think you'll find it's pretty straightforward. I just thought I'd post a little video to kind of clarify that. So yeah, just to summarize, I think the way that problem is worded in the book is a little I don't want to say sketchy. It's just on the initial assignment I should have clarified that we're only going to be looking at end-plane stresses. So that's what's going on in the updated posting on Blackboard. And I think you'll find that with these 2 hints, this problem's pretty doable. All right, that's all I got. I will see you all in class on Thursday.